but it's not the only one. And angles may be defined totally differently, so I wanted to be continually on the lookout for that. But in this case, we're following the standard convention. And standard convention is that angles are measured positive as you go counterclockwise with respect to your reference. Okay? So the question is now, based on the information you have on this plot, what can you tell me about the length of this component of x, and what can you tell me about the length of this component of y using simple trigonometry? So go for it. Yeah.
So the x component of b would be b cosine theta, and the y component of b would be b sine theta.
So hopefully this is reasonably familiar to most of you. I've set this up by definition so that I've got right triangles, and therefore I can use standard trigonometry relations. Reminder of the mnemonic that allows us to remember this most simply. And again, I would strongly encourage you to use this with opposites and adjacents and hypotenuse, defined with respect to wherever your angle is defined. Here it's with respect to the horizontal, but it will not always be. So keep that in mind. You'll see what I mean by this as you get confused in the next few days. So the mnemonic that tells us the relationship between opposite, adjacent, and hypotenuse, there it is, so SOHCAHTOA. And indeed, this one then, because the cosine of this angle is the adjacent over the hypotenuse, the cosine of this angle is the adjacent over the hypotenuse. So the adjacent length, which is the x component, must be b cosine theta. And the y component, which is the opposite length, must be b sine theta. So this is the idea of the components of this vector on the Cartesian x and y coordinates. Okay, easy enough. Let's take a second vector, start mixing things up a little bit. Maybe I'll do it here. So here's now a c vector. I'm going to draw this so that it doesn't look even close to at 90 degrees to the other one. Here's the c vector. And again, I'm going to project this into components along the x direction and along the y direction. So these are the components in x and y. Again, by definition, I'm making right triangles here so that it projects perpendicularly onto the x and y axes. So, the question is here, how might the angle of this vector be defined? Well, if I was being strictly consistent, it's quite possible that the angle of this vector c would again be defined with respect to the positive x-axis. So this, in fact, I might call an angle phi. It's all the way around from the plus x to the c vector. And then the question possibly gives rise to a little bit of confusion, maybe not, is what are the components? Well, it's still true that the components of this one are, I'm trying to color consistency here, cx is c cosine phi in this case, and cy is c sine phi. Now, phi is now an angle between 90 and 180 degrees, or between pi over 2 and pi, depending on what unit system you like. That will tell you if you plug in some imagined numbers, or if you kind of remember the dependence of this thing. If I've got an angle phi which is between 90 and 180 degrees, and I want to find out its cosine, it's going to turn out to be a negative, right? Which is good, because it looks as though the projection or component of this thing is in a negative vector. So this builds in for us directly the sine of the component if we're measuring the angle as shown with respect to the plus x-axis. All right, so how does this help us when it comes to adding multiple vectors in 2D? And if we're adding multiple as opposed to just two, it really does help us. What we're going to do is when we've got multiple vectors, we're going to resolve each vector into x and y components. And we are going to then add or superpose then we have to reconstruct the resulting. Okay, so we've only got 5 minutes left, and I think I'm tempted to try and make you do some work on this with an example. So hopefully again, this is reasonably familiar piece of vectors. I'm going to give you a problem of 2 vectors in 2-dimensional space and ask you to solve it. Okay, so let me just be as quick as I can in getting this set up. Here's an example. We've got a vector M as a magnitude of 4.75 centimeters at 58 degrees counterclockwise. I'm not going to write the whole thing, it's a waste of time. From plus x-axis. We've got a second vector n, which we don't know, and you're about to find out. But I'm going to tell you the resultant, which is m plus n, also has a magnitude of 4.75 centimeters. And in this case, is at 39 degrees counterclockwise from the plus x-axis. All right, so again, I'm not going to give you too much guidance on this because I'm hoping many of you have done these sort of exercises before. And for those of you that haven't, hopefully you'll find somebody sitting next to you who's done it. I'm going to ask you in the remaining 3 or 4 minutes of class to tell me what vector n is. Okay? So I've given you the definition of vector n, which is one of 2 vectors we're going to add together. We don't know n yet, but we know the resultant, n plus n, as this parameters. So I'm going to see if you can, in just a few short minutes, figure out what vector n is. Okay, go for it.
4.75 one that is like 4.7, the second one, R. Huh? Oh, 39? Okay, so just do 4.75. Oh, you need.
You might find it useful to draw what you know to begin with.
None of us got it. I just got the Do you have the Good job, dude. Moral support.
Maybe you can just look at it.
Oh my Oh, my Tony. Well, you did this, right? This one's that.
So we won't have time to complete the calculation, but what I'm most interested in is exploring if you have the
Look at that.
strategy right in figuring out how to get an answer. We'll start with about 30 seconds and just talk about how we would determine this, and I'm going to say the actual end of the calculation, just for you to look at in my notes. If any of you are unsure, talk to a neighbor. You know, I'm going to promote learning from your peers. Useful thing to do. Okay, so it's a relatively short problem. Who's going to help us out in figuring out how we figure out what n is? What do I need to do? Yeah.
Oh, wait, you can't. Oh, but yeah, you can.
Okay. So first off, break up each vector into components. Okay, so let me paraphrase what you said, all of which is correct. So I'm going to work with components, so I need to find the components of the vectors that I know to begin with. I know n and I know r, so I can find their components of x and y. So, okay, we call this one theta, we call this one phi. And so nx is n cosine theta, this is n sine theta, r cosine phi, this is r sine phi. I know all of these four pieces of information. I know magnitudes, I know angles, so I know all of these. I can put in numerical things, I'm not going to do that in class, it's not important. What I need to do now is recognize that r equals m plus n. And so I can also say that rx equals mx plus nx, and ry equals ny plus ny. And I can rework this. So this is rx minus mx. This is ry minus my. Once I've got these, I've now got the two components of my n vector. And if you reconstruct it, of course, you can see what you can see visually is that this should go something like that. Okay? So we're out of time. I don't want to keep you guys any longer. Take a look at the answer in my solutions. The other thing before you go, I would like you all to read the remaining sections on unit vectors and vector scalar products of vectors before we meet again next Tuesday. Okay, have a good weekend. I will see you on Tuesday.
Okay.